I'll give you a chance to read the problem. You can pause the video. Okay, so we have 8 cubes with side length k, where k ranges from 1 to 8. So we're trying to find the total number of towers that can be constructed using these two rules. Now, a common strategy in counting problems is to start from a simple case and work up recursively. So let's try the simplest case possible and see if we can build up. So cubes and number of towers. Let's make a little table. So in the case of just having the cube of length 1, clearly there is only one tower. What if we have the cube of 1 and 2? When in this case, there are clearly two towers, since both 1, 2 and 2, 1 works. And my notation here is this listing denotes the order of cubes from lowest to highest. So this would be the bottom cube, and this would be the top cube. 1 would be on bottom, 2 would be on top. So in this case, we have two towers. If we add a third cube, cube of length 3, then there are 3 ways to insert the cube of length 3. And all of them work, since the upper bound here is 2 plus 2 equals 4, since one of our rules is the cube immediately on top of a cube with edge length k must have edge length at most k plus 2. And the limit here is 1 plus 2 equals 3. So 3 can go here, 3 can go here, 3 can go here, since any cube can go there. So these are 3 possible ways to insert 3 in any permutation of 1 and 2. So the number of ways for this to happen is just perhaps organize a little better. 2 times 3 equals 6. All right. What about if we add a fourth cube? If we add a fourth cube, then in any permutation, there is clearly one insertion that doesn't work, right? Because the upper bound of 1, the one next to 1, is 1 plus 2 equals 3. So 4 cannot go there. But 4 can go in any other slot, since this upper bound is 4, this upper bound is 5, and any cube can go here. So 4 can be inserted in any 3 of, sorry, not this slot, but any 3 of these slots. This one, or this one. Okay, so the total number then is for every permutation of 1, 2, and 3, we can insert 4 in 3 ways. So this gives us 18 ways so far. What about 5, if we added 5? Well, in this case, we have a similar construction, right? We just follow as earlier. But in this case, we can't insert here and we cannot insert there. So these don't work because the upper bound here is 3, the upper bound here is 4, but we can insert everywhere else. So it seems like after we pass this initial multiplication by 2, every successive addition of a block yields a multiplication by 3, because there are 3 ways to insert the next block. And we can show this in the general case by noting that, so this would be 2 times 3 cubed, which would be 54. So we can show this in the general case by considering 1, 2, all the way up to m, m, and it's clear that m plus 1 can be only inserted here, since anything can, and next to m minus 1, since the upper bound here is m plus 1, and next to m. So there are 3 ways of inserting m plus 1 in a sequence from 1 to m, some permutation of 1 to m. So in total, since we're going to, after we go to 2, we have 8 cubes. We have two ways, obviously, to do the first 2, and then we want to insert 6 more, right? So by a recursion, this should be 2 times 3 to the 6th, which is given as 1,458, and mod 100, that's 458, which is our answer.